Greetings and welcome to the online lecture series of HVAC and R, that is Heating, Ventilation, Air Conditioning and Refrigeration Engineering. This is elective 1 of BA Mechanical 2015 course, part 1. Due to COVID-19 situation, it is not possible to conduct the classroom teaching. So we have shifted our teaching process to online teaching process. So all the lectures are made as per the SPPU syllabus. This is the first online lecture on unit number 1, that is Advanced Vapor Compression Cycle. And in today's lecture, we are going to cover Transcritical CO2 refrigeration cycle. Refrigeration and air conditioning systems are most extensively used devices in domestic sector as well as in commercial sectors. These industries are mainly facing two important crises, that is energy crisis and environment crisis. Energy crisis because of its increase in use, almost 40 to 45% energy is consumed through these devices. So it is very much essential to focus on how to conserve this energy, how to save this energy by developing more efficient devices like heat exchangers, compressors, piping like that. And secondly, environment crisis. Most of the gases used in refrigeration system, which are used as a refrigerant, they harm the environment. They increase the global warming potential, as well as they deplete the ozone layer as well. To overcome this environment crisis, new refrigerants are coming up. The CO2 is also one of the refrigerants, which is environment-friendly refrigerant, which has 0 ODP and 0 GWP. And but there are some challenges to use CO2 as a refrigerant. If we overcome these challenges, the CO2 becomes a potential substitute for R12, R22, and HFC 134A, because CO2 is mainly compatible with the normal lubricants. It is also compatible with the normal materials used in construction piping. It is non-flammable, it is non-toxic, greatly reduced the compression ratio, easy availability, high volumetric refrigerant capacity, and excellent heat transfer characteristics. So these are the advantages which encourages the practitioners to use this CO2 as a refrigerant. But it has a major drawback that its critical point is very low. And that's why when we use CO2 in a conventional vapor compression cycle, then the cycle becomes a transcritical cycle. So this is a basic transcritical cycle. Let me clear what we understand by transcritical cycle. The conventional vapor compression cycle, it is also called as a subcritical cycle. Subcritical cycle means if both processes happen below critical point, that is evaporation process and condensation process. If both processes happen below critical point, that is called as a subcritical cycle. But if one of the processes happen above critical point, like in this cycle, then it is called as a transcritical cycle. So when CO2 is used as a refrigerant in conventional vapor compression cycle, the cycle becomes a transcritical cycle. That means the condensation process happens above critical point and evaporation process happens below critical point. This is because CO2 has a very low critical point. Its critical point is 31 degrees Celsius. So generally the condensing medium used in practice of temperature about 30 to 35 degrees Celsius. So it is very difficult to achieve the condensation process in normal vapor compression cycle. So that's why when we use CO2 as a refrigerant in conventional system, it becomes a transcritical system. So first of all, we will try to understand what is this transcritical cycle. Like conventional refrigeration system, it has also a 4 basic component, like compressor, gas cooler. So here, instead of condenser, the condenser is replaced by gas cooler, expansion device, and evaporator. So we start from point number 1. So point number 1 is on the saturation curve. So 1 to 2 is the compression process. So if it is ideal compression process, it is isentropic compression process 1 to 2s. Practically, it is 1 to 2. At point 2, refrigerant is a superheated high pressure refrigerant. Then that it enters into the heat exchanger. So in conventional system, this heat exchanger is called as a gas condenser because condensation process occurs there. But here the condensation process doesn't occur. That's why this particular heat exchanger is called as a gas cooler. So 2 to 3, during this process, the gas is being cooled isobarically. So at point 3, it's a slightly low temperature gas, but still high pressure. Then 3 to 4, the refrigerant expands into the expansion valve, and that process is isoenthalpic process. 4 to 1 is the evaporation process, which is a normal evaporation process because it happens where the heat is absorbed from the cooling medium, or heat is absorbed from the substance or space which is to be cooled. So this is a basic transcritical cycle where except 2 to 3 process, remaining processes are same. Like 2 to 3 process in normal conventional vapor compression cycle is condensation process. Here it is a gas cooling process. So other factors remain same. This basic cycle has certain drawback. Mainly, there are huge expansion losses compared to the conventional refrigerants. So how these expansion losses occur, we will see. So this black line cycle is a conventional vapor compression cycle. So 1 to 2 is, sorry, blue line is a conventional vapor compression cycle. So this is compressor, this is condensation because it happens below critical point, then expansion, isoenthalpic expansion, and then evaporation. And we use CO2 as a refrigerant, then this cycle is changed to transcritical cycle. Means there is no condensation because the critical point is low of the CO2. So compression, then gas cooling, then expansion, and then evaporation. So if you compare these two cycles, you will realize. So the point number, this is point number 4. Suppose this is point number 1, point 2, point 3, and point 4. So the point 4 lies close to the center of this particular saturation curve. So that is wet region. And point 4 in conventional cycle, it is close to the saturated liquid line. So if we see the dryness fraction at this point and this point, there is a huge difference. Dryness fraction at conventional system, that is, you see this cursor. So here the dryness fraction is around 0.15 to 0.2. Here the dryness fraction is around 0.4 to 0.5. So that means almost 15 to 20% only gas is, refrigerant is vaporized, and that refrigerant doesn't take part in refrigerant effect during the evaporation process. So there is 15 to 20% evaporation losses that is already happened in conventional system. But these losses are more in transcritical cycle. Almost these losses increases to 40 to 45 or 50%. That is a huge expansion losses. And generally this process where in the expansion process the refrigerant vaporizes, this process is called as a flashing of refrigerant. So this is happening. So this flashing of refrigerant in transcritical cycle is huge. And because of this flashing, there is a huge expansion losses. So that is the major difficulty or major disadvantage of this transcritical cycle. So in order to use this particular system in practice, or in order to improve the performance of this transcritical cycle, it's very much essential to minimize these losses. So how we can minimize these losses? So all the modifications to be made, this modification must result into a shifting of this 0.4 towards left. So even 10% shifting of this point increases COP by 10%. So the cycle needs modification for better performance. So that's why the basic transcritical cycle is not used in practice but the modifications are made, and there are 6 modifications we are going to discuss in coming lectures. Today's lecture we will only focus on basic cycle, but this is the major drawback of basic cycle, because due to this huge expansion losses compared to the conventional refrigeration cycle, the cycle needs modifications. So practically the CO2 system used at various sectors, commercial sectors as well as domestic sectors. So these are some glimpses. This is the first store in Russia which works on transcritical refrigerant. So these are some models of refrigeration systems commercially used of capacity of 100 to 1000 TR using CO2 as a refrigerant, because CO2 is economically easily available and it is also environment friendly. So some developed countries are already adopting CO2 as a refrigerant. The only thing is that the piping required is very heavy, because if you see the pressure ranges are very high. Even at this particular pressure, the pressure is around, so this is pressure enthalpy diagram. So the pressure is very high. So the pressure is around 80 to 90 bar pressure is required. Here also pressure is around 25 bar evaporating. So the pressure handled by the system is very high. So the thick piping is required to overcome that pressure. So this is practical examples. So CO2 is also used in automobile sector because of its low specific volume. The specific volume of CO2 is very low. Even it is 50% of the specific volume of R22, because R22 is being extensively used in automobile industry. Now the R22 is replaced by HFC 134. But even the specific volume of CO2 is even less than that of almost 0.5 times the specific volume of R22. So it is preferred in automobile industries as well. So Mercedes-Benz, this is one photograph where the Mercedes-Benz equipped with the CO2 air conditioning system, and testing is being carried out here. Air conditioning testing is being carried out. CO2 is also used in transport refrigeration, but that is a different part. That CO2, that dry CO2 is being used. So when during transportation of the food or preservations, so when it comes in contact with the heating objects, it gets evaporated, directly converts into vapor. So some transport vehicles also, transport refrigeration also CO2 is used. This is slightly different here. The liquid CO2 is being used for cooling, and due to cooling, it gets evaporated and it exhausted out. So at the end of this particular topic, we should be able to explain the basic transcritical cycle. We should be able to explain what are the drawbacks of the basic cycle, and how to overcome this drawback. That we are going to study in next lectures, in different types of CO2s. Why CO2 becomes a potential substitute? If you have listened this lecture carefully, that you will be able to answer this. Why CO2 is being used as a potential substitute. You should be able to quote some applications of CO2 refrigeration as well that we have just seen. I hope you have understood this particular lecture. Thank you very much, and looking forward for next lecture. So next lecture we are going to cover the different types of CO2 refrigeration system as well. Thank you very much.